Hello everyone, welcome to the channel Knowledge for You. Today I am going to discuss one of the most important 5-mark question of electronic devices subject. So this question is from second unit, that is power supplies, and the question is explain the working of Zener diode as a voltage regulator. This is a symbol of a Zener diode. So here we have a symbol like Z symbol. So this is the cathode terminal negative and this is the anode terminal positive. This is the ideal symbol of Zener diode, but when it comes to practical symbol, so this is a practical symbol. Usually we replace Zener diode with a voltage across it, that is Vz is the voltage across it, and along with the internal resistance, that is Zener resistance. This is the cathode terminal and this is the anode. So usually Zener diode operates in reverse bias. So first we will see what is the difference between a diode and a normal PN junction diode and a Zener diode. So Zener diode is a specially designed PN junction diode. Zener diode is a specially designed PN junction diode that operates in reverse breakdown region. It is a specially designed PN junction diode that operates in reverse breakdown region. Then in forward bias, Zener diode behaves like a normal PN junction diode, but in reverse bias only, the main function of Zener diode comes into picture. In reverse bias, it acts like a voltage regulator. It is widely used as a voltage regulator in the power supplies to provide the constant output voltage. This is the important application of Zener diode in reverse bias. It is used in reverse bias as a voltage regulator to provide the constant output voltage. It is a specially designed PN junction diode. Specially designed in the sense to a normal PN junction diode, if the doping is done, doping means what? The process of adding impurities. If the high amount of doping is done to a normal diode, then it becomes a Zener diode. So that's why it is written as specially designed PN junction diode that operates in reverse breakdown region. It is used as a voltage regulator in the power supplies to provide the constant output voltage. Now we will see the circuit description and the working of Zener diode as a voltage regulator. So this is a circuit diagram of a Zener diode we have. This is the unregulated power supply. This is the series resistance or the source resistance we have. Here the Zener diode is connected in shunt. Here shunt nothing but parallel to the load. Here we have used a load as RL resistor. So this Zener diode is connected in parallel to the load resistor RL. So this is a power supply. Here unregulated power supply means unregulated in the sense here we are not providing the constant voltage, and now we are applying it to a Zener diode so that we can get the constant output voltage. So the current flowing to the source resistance or the series resistance is given as IS, and next the current flowing to the Zener diode is IZ, and the current flowing to the load resistor is I. Now look at here. In this circuit, this current, there is a series current and a source current, you can say instead. IS, this current after coming to this node, it is getting divided into two branches. One is IZ, second is IL. So here IS is equals to IZ plus IL. Now here our intention is to make the output voltage constant. Here the target is we have to keep the output voltage constant. So for that we are discussing two cases here. So look at here, circuit description. In a Zener voltage regulator circuit, that Zener diode is connected in reverse bias across a load resistance RL. A series resistor is connected in between the unregulated supply and the Zener diode. In between the unregulated supply and Zener diode, a series resistor is connected. It is also known as current limiting resistor. It is also known as current limiting resistor. Why it is called as current limiting resistance means here unregulated means here we can vary the input voltage. So if the input voltage increases or decreases, that effects also occurs on the current. So if the current increases, then the excessive drop is going to be takes place across the series resistance. So it is going to limit the current. That's why the name is given as current limiting resistor. So let's see the two cases of a Zener diode. The first case is regulation with varying input voltage. Here we are discussing two cases. For the first one is what happens if the input voltage varies. At that point of time, the output is considered as the fixed one. The RL is treated as a fixed output. And the second case, input we are keeping fixed but varying the load current. So these are the two cases we are discussing. The first case is regulation with varying input voltage. So if the input voltage varies, see here, if the input voltage is varies, then the input current, that is series current, also varies. For less amount of input voltage, less current flows. If we increase the input voltage, then more amount of current flows to this. Then here at this node B, the current IS is divided into two parts. One is IZ, second is IL. IZ is the current flowing to the Zener diode, IL is the current flowing to the load resistor. So if input current, as the input voltage increases, if the input voltage increases, then this current IS also increases. IS current also increases. So for example, if the IS current is 5 amps, then it will be divided into like this, like IZ will be 3 and IL is what? 2 amps. 3 plus 2 is equals to 5. If we increase the input voltage, assume that IS becomes 6 amps, then in that case this T2 should be fixed. This load current should be fixed. It should not be altered. It should not be changed. So in that case, ultimately the effect is going to be occur on only IZ current. Then IZ will be 4. So like this, if the load is constant, load is fixed, this IL current is also fixed. The only change is going to be occur only on IZ. That's why it is given as, assume the load resistance RL is fixed and the input voltage is varied with respect to the limit, within the limit. And when the input voltage increases, then this IS current also increases. If this IS current increases, its effect will be occur on IZ. So IS increases. Then increase in the current will be this increase in IZ current. So if IS increases, IZ also increases, then this current will be bypassed through the Zener diode and this load current remains at the fixed amount, that is 2 amps. That's how it is maintaining the output voltage constant, because IL is fixed at 2 amps and load resistance value is fixed. For example, assume it is a 1 kilo ohm, just for example I am saying. So if you multiply these two, then output voltage V0 is equals to IL into RL. So it will be what? IL into RL means it will be 2 amps into 1 kilo ohm. So it will be what? 2 volts. See here, if we increase the input voltage, then IS current increasing, but IL will be remain at 2 amps only. The effect is occurring only on IZ. The excessive current will be bypassed through the Zener diode. That's how it is going to maintain the output at fixed amount of voltage. So if input voltage increases, IS increases. If IS increases, IZ is increases. Therefore, it maintains the output voltage VL constant. Next case we have case 2. Regulation with varying load current. Now what happens if load varies? If IL varies, what happens? So assume that the input voltage is fixed. So in this case, input is fixed and the load current is varied by changing the load resistance RL. So as the load resistance decreases, that means we are varying here RL. So R is variable now. RL is variable now. Now it is at fixed value. So if the RL decreases, then what happens? We have a relation like RL is equals to V by IL. If RL decreases, then IL increases. Okay, then IL increases. Then as per the relation we have, IS is equals to IZ plus IL. So this value is fixed now. So if IL increases, so as the load current decreases, this load resistance decreases, the load current increases. So this increase in the load current, it is equal to what? If IL increases, ultimately IZ should be decreased to maintain IS fixed. To maintain IS fixed. So just like the reverse case of the first one, if IS is fixed at 5 amps and IL is increasing like 3 amps, then it should be what? 2. Again IS is fixed, then IL should increase like 4 plus it should be at a limiting value, that is 1. So the ultimate effect is that IL increases when RL decreases. This increase in the load current is equal to decrease in Zener diode current, and the excessive amount of current will be dropped across the IS-RS. Okay, and IS-RS drop is a constant because IS value is fixed. So that's how it maintains the output voltage constant though the load varies. So finally it is clear that if RL decreases, then IL increases. If IL increases, IZ decreases, and this VL remains constant. So that's how the Zener diode acts like a voltage regulator by maintaining the constant output voltage. So just 2 cases we have. In the first case, if input voltage varies, so look at here, just within a single line I can conclude that. So in the first case, If input is increases, then IS series current increases. If series current increases, then what happened? This IZ should be, the IZ current should be increased and VL should remain constant, because IL should be remain constant. The first case. And the second case is if Vn is fixed. If Vn is fixed, so ultimately the load resistance is changing. If RL decreases, then what happened? IL increases. If RL decreases, IL increases. If IL increases, then IZ should decrease. As per the relation, IS is equals to IZ plus IL. If IL increases, IZ should decrease by maintaining the constant output voltage. So that's it from Zener diode as a voltage regulator. Thank you.